Welcome to the High Voltage AI Podcast. Today is Tuesday, and we are really embarking on an in-depth exploration. It's a truly foundational topic for every electric utility engineer out there, we're calling it. From 4% to 15% grid consumption in 6 years. Now, this deep dive, it's a key part of our week-long series. You can find it featured in the PXRD newsletter on Substack. And if you're not familiar, PXRD is really your go-to source for daily insights, for analysis on critical grid infrastructure, and, the evolving challenges we all face. Our overarching goal with this whole series is to educate you, our listener, on overhead and underground construction types, why we use them, their unique characteristics, especially in today's rapidly changing energy landscape. Yesterday, we kicked things off talking about the data center tsunami hitting 75% of utilities. And today we're really zeroing in on the staggering, almost unbelievable growth in electricity consumption that these centers represent. It's a core problem. It really demands a complete rethink of how we approach grid planning.
So to help us navigate this monumental shift, we have our expert guide back with us.
Yeah, it's great to be here and good to continue that conversation we started yesterday. Because the scale of this data center surge, it's really something. And the striking thing is it's not some, far-off future problem. It's happening right now. It's expanding rapidly. Let me give you a concrete example, one that really brings it home. Microsoft. They recently went to Dominion Energy in Virginia, and they asked for 1.5 gigawatts of capacity.
Wow.
For a single data center campus.
1.5 gigawatts, just one campus.
Exactly. To put that in perspective, that's enough to power roughly 1.1 million homes.
That's incredible.
Think about the largest city in your service territory. And imagine adding that kind of demand from just one customer. And look, this isn't some isolated case. It's not an anomaly. Across the U.S., 75%. A full 75% of major utilities are reporting this kind of unprecedented data center demand on their systems. So this isn't just, adding a bit more load here and there. It's fundamentally reshaping how we approach grid planning, distribution design, investment, everything. I'd argue, actually, that for our industry, this is probably the most significant concentrated load growth challenge we've faced since the original electrification of the country.
That's a huge statement.
We are genuinely in uncharted territory here.
1.5 gigawatts. I mean, that figure is just mind-boggling. It really makes you wonder, are we as an industry truly ready for this? Is this tsunami, as we called it yesterday, hitting us full force? Or is there still time to adapt? Can you give us some more specific numbers, like the hard data that really quantifies this consumption surge?
Absolutely. And let's break down those numbers, because they really are rewriting the load forecast models that utilities have, relied on for decades. Okay, so data center electricity consumption, it surged from just 4% of total U.S. electricity use back in 2022.
Okay, 4%.
Right, to projections now of a monumental 11 to 15% by 2030.
Wait, 11 to 15%. By 2030? That's only 6 years.
Exactly. A massive leap in just 6 years. And remember, typical national load growth might be, 1, maybe 2% a year. This trajectory is it's completely off the charts. To really sort of grasp the scale, think about this. The projected increase just from data centers over the next, say, 8 years. It's roughly equivalent to adding the entire electricity demand of California.
The whole state of California.
The whole state. Added to the national grid. Imagine trying to build out the generation and transmission for that in such a short time frame. And what's also really fascinating here, and what creates huge engineering headaches, is it's not just the total usage, it's the concentration and the timing. Unlike, traditional industrial growth that might spread out over regions, over years, data centers tend to cluster. They group together in very specific markets.
Right, like Data Center Alley.
Precisely. Northern Virginia, Data Center Alley, host over 25% of the global data center capacity.
25% globally in one small area.
Yeah. It creates this immense localized grid strain. It forces utilities there to completely rethink their entire infrastructure strategy. And these aren't, your typical office building loads either. We're talking hyperscale facilities. They routinely require 50 to 200 megawatts.
50 to 200.
Of continuous capacity, 24/7, 365. And they demand incredibly high reliability, 99.99% or better. Now, contrast that with, say, a traditional large manufacturing plant. Maybe 5 to 15 megawatts peak demand, more flexible hours. You see the difference immediately. You see why utility planning departments are facing such a unique challenge.
Yeah, that concentration and that relentless continuous demand, it really hits home why our traditional planning methods, which, let's face it, were built for a different era, are just struggling to keep up.
Yeah.
So for the engineers listening right now, where specifically are those old playbooks falling short? What parts of our existing grid are most exposed by these new demands?
That's a really important question. And it's where, the rubber meets the road for the engineers on the ground. The challenges, they go way beyond just needing more power. Data centers create this kind of perfect storm of design complications. They fundamentally expose the limits of our grid architecture, our planning processes. Okay, first up, load density. Our traditional distribution planning, it usually assumes maybe 1 to 3 megawatts per square mile, even in dense commercial areas.
Right, that sounds familiar.
Well, a data center can cram 50 to 100 megawatts into a single facility, often on just a few acres of land.
50 to 100 megawatts on one small plot.
Exactly. That's an order of magnitude jump in power density
Yeah.
over a tiny footprint. Our distribution systems, frankly, just weren't designed for that kind of localized load. Second, and this is critical, reliability requirements. Okay, most big industrial customers might be okay with 99.9% reliability, which sounds pretty good, doesn't it?
Yeah, 99.9 sounds great.
Right. But data centers demand 99.99%, or even better, 5 nines sometimes.
Okay.
That extra 0.09%, it's not just a number. For engineers, it's a total paradigm shift. It means going from, say, 8.76 hours of acceptable downtime per year down to just 52.6 minutes.
Wow. Less than an hour a year.
Per year. So this isn't about small upgrades. It demands a fundamental rethink of redundancy, backup systems, N-1 contingency planning. You can't just plan to fix it fast when it breaks. You have to engineer it so it basically never breaks. Third thing, timeline compression. Look, traditional utility planning for big projects, new substations, transmission lines we operate on, 3 to 5 year horizons, sometimes even longer for major transmission.
Sure, that takes time. Permitting construction.
Exactly. But data center developers, they often expect energization within 18 to 24 months of their initial request.
18 months for potentially hundreds of megawatts.
Yep. It forces utilities into this position where they almost have to speculate on infrastructure needs, starting massive, multi-million, sometimes multi-billion-dollar projects before the demand is even fully confirmed, just to meet these hyper-aggressive timelines.
That's a huge risk shift.
It's a massive shift from our usual reactive planning to something much more proactive, almost speculative. And finally, that geographic clustering we mentioned. It's not just about local strain. It creates serious, localized transmission bottlenecks. And you can't solve those with traditional load balancing tricks.
Right, you can't just reroute power easily when it's all needed in one spot.
Exactly. When a quarter of the world's capacity is in one small region, you need completely new transmission corridors, significant grid reinforcement, just to serve that highly concentrated and still growing demand.
Those are undeniably serious engineering hurdles. It sounds like it's completely reshaping what used to be a relatively predictable planning cycle. So let's bring it down to the ground level. What does this all mean for the utility engineers listening to us right now? How are these challenges hitting their daily work, the decisions they make every day, the tools they use?
Yeah, this is the engineering reality check. For those on the front lines, the impacts are, they're everywhere. First, think about distribution design. Your standard 12.47 kilovolt, maybe 25 kilovolt systems, the workhorses for decades, they might just be inadequate for these huge data center loads.
So the standard voltages might not cut it anymore.
In many cases, no. We're seeing utilities actively looking at 69 kilovolt, even 138 kilovolt direct connections right to the facility for loads over 100 megawatts.
The right transmission feeds, essentially.
Basically, yeah. And that fundamentally changes distribution system architecture. It needs different equipment, different clearances, different protection schemes, things many distribution engineers aren't used to designing routinely. Then substation planning, that traditional annual load growth, maybe plus or minus 2% a year, forget about it.
Right.
It's being completely replaced by these huge step changes, 50, 100, 200 megawatts coming online almost overnight as a single data center powers up.
So your substation planning goes out the window.
Pretty much. Imagine planning for gradual growth, and suddenly you need to triple a substation's capacity. It forces entirely new approaches to sizing transformers, bus configurations, protection, rethinking site selection, physical layout, just to fit the bigger gear. Next up, transmission upgrades, that clustering we talked about. It's creating such deep transmission bottlenecks that it's forcing billion-dollar upgrade programs.
Billions with a B.
Absolutely. Just look at the PJM interconnection queue. That covers 13 states plus DC, right? It currently has over 2,600 gigawatts of proposed projects waiting.
2,600 gigawatts, that's astronomical.
It is. And while that's not all data centers, they represent a very significant chunk of those new requests. They're driving the need for new high-voltage lines, new substations, major overhauls of existing infrastructure. It's not just adding a line here or there, it's re-engineering entire networks. And finally, for the protection and control engineers, those super high reliability requirements, the unique load profile of data centers, it's forcing a fundamental rethink of existing protection schemes.
Okay, how so?
Well, we're talking about automatic transfer systems that need to switch in milliseconds, not seconds. You absolutely have to ensure grid stability when these huge loads suddenly come online, or, just as importantly, trip offline.
Right. A sudden loss of 100 megawatts could cause problems.
Big problems. So your SCADA systems, your relay settings, even your grid-wide stability analyses, they're all under intense scrutiny. They need new, more sophisticated solutions to handle these dynamics safely and reliably.
Wow. It's truly pervasive. It touches every single aspect of utility engineering, from the local distribution wires right up to the bulk transmission system. Okay, so we've talked about the enormous, the scale of the demand, and the painful how it's impacting grid design. But what's really fascinating to me, and I think what our listeners really want to wrap their heads around, is the why. What is behind this sudden explosive growth? Is it just one big thing, or is it like a confluence of forces driving these crazy numbers?
It's definitely a confluence, several powerful forces hitting all at once. And if we kind of connect this to the bigger picture, there are maybe 4 key drivers that every engineer really needs to understand. The most significant one right now, perhaps the newest big accelerant, is artificial intelligence.
AI.
Yes. Training these models, running inference workloads, it's incredibly energy intensive. Just to give you an idea, training one large language model, just one, can eat up over 1,000 megawatt hours of electricity.
1,000 megawatt hours.
Yeah, that's like the annual electricity use of about 90 typical American homes.
For training one AI model.
Exactly. And that's just the training. As AI gets embedded everywhere, generative tools, optimizing complex systems, that immense continuous energy demand just keeps growing. And these aren't peak loads, remember. They run 24/7, baseline.
Yeah.
Okay, second driver, the ongoing and actually accelerating cloud migration. The big shift from companies running their own servers in, dusty closets.
Right, the on-prem stuff.
To using massive, centralized cloud computing facilities. Amazon, Microsoft, Google, it's still happening fast. Think about it. Every app you use, every video you stream, every online service, it all runs in a data center somewhere.
True.
So this fundamental shift just concentrates the power demand into these huge facilities rather than lots of smaller distributed loads. Third one, and this might seem counterintuitive to some, edge computing.
Edge, wouldn't that reduce central demand?
You'd think so, right, moving processing closer to the user. But in reality, edge computing is actually multiplying the number of facilities needed across the grid.
Yeah.
It doesn't really reduce the total demand much. These edge sites still need power, often with high reliability. And they still connect back to the big hyperscale hubs for core processing and storage. So you're basically just adding more nodes, more points of demand across the network. It's an expansion, not really a decentralization of the total load. And finally, a major accelerant, something that really compressed years of growth into months, was the surge in digital infrastructure investment, especially triggered by the pandemic.
Right. Everything went online overnight.
Exactly. The pandemic forced a level of digital transformation that might have otherwise taken 3, maybe 5 years. It happened almost instantly. This compressed what should have been gradual infrastructure growth into this highly concentrated surge, hitting utilities with this wave of unprecedented demand all at once. Left everyone scrambling to catch up.
That paints a really comprehensive picture, and frankly, a rather daunting one, all these forces converging. So let's bring it back to the utility engineers listening. What's the ultimate bottom line here? What's the key takeaway they should walk away with from this deep dive into data center grid consumption? What's the one thing that really needs to shift in their mindset or their approach?
Yeah, the bottom line, I think for every utility engineer listening, it's this. This is not a temporary surge. It's not going to level off or go away. This is a structural, permanent shift in how electricity is being consumed. And it requires fundamental systemic changes to how we design, plan, and operate the grid, period. The utilities that seem to be adapting fastest, they're the ones treating this massive data center load growth as a primary design constraint, a core part of their long-term strategy, not just, an exception they have to somehow accommodate. So, my actionable advice, based on everything we've discussed, it would be this. For distribution engineers, start modeling 50-plus megawatt single-point loads in your planning scenarios now, even if you don't have confirmed projects knocking on your door yet. Proactive readiness is absolutely key. Think beyond the usual commercial feeder designs.
Get ahead of it.
Exactly. For transmission planners, look, the days of just incremental capacity additions are, they're largely over in these high-growth regions. You need to plan for step-change load growth and really consider how clustering impacts your whole regional transmission network. You might need entirely new corridors, major grid reconfigurations.
Bigger picture thinking.
Much bigger. And for protection and control engineers, it's critical. Start evaluating how your existing schemes, your relays, your automation handle these large, sudden load changes, additions, and removals. You need to adapt to the unique electrical characteristics and, of course, those ultra-high reliability demands. Look, this is probably the biggest challenge our industry has faced in decades, but, it's also the biggest opportunity. Because the utilities, the engineers who successfully solve this data center puzzle, they will, without a doubt, be the ones defining the grid of the future.
That's a powerful message and an essential one. We've really taken a deep dive today into the just stunning growth of data center electricity consumption, what it means for our grid, going from 4% to maybe 15% in just 6 years. This has been a truly foundational part of our week-long series. Now, looking ahead, tomorrow we're going to get even more technical. We'll dive right into distribution design when 50 megawatts becomes normal.
Mm-hmm.
And just to give you the full context for the week again, Monday was the data center tsunami hitting 75% of utilities. Today, Tuesday, we covered from 4% to 15% grid consumption in 6 years. Tomorrow, Wednesday, is distribution design when 50 megawatts becomes normal. Thursday, we'll tackle the big picture with transmission planning bottlenecks and queue crises. And then on Friday, we'll bring it all together, focusing on practical engineering solutions that actually work. So, as you head back to your work today, maybe mull this over.
The question really isn't whether data centers will reshape utility engineering. It's whether we, as an industry, will lead that transformation or just end up scrambling to catch up. If you'd like to leave feedback or if you have any questions on today's deep dive, please feel free to reach out to us. You can email me at alex.reed.power.podcast@gmail.com, or you can reach our expert at emma.quinn.power.podcast@gmail.com. We'd love to hear from you. Thanks for tuning in.